Welcome back. In this video, we're going to look at examples of using the root test for series. Let's get to it. All right, so here's our first example. We want to determine if the series converges or diverges. And our first series is this series right here, the sum from n equals 1 to infinity of 1 divided by n to the power of 3n. All right, now whenever you see a series that has some value raised to a power of n, it might be a good idea to try and use the root test. And the root test says this. For a series where you have the sum of the terms of a sequence a sub n, if the limit as n approaches infinity of the nth root of the absolute value of a sub n is equal to some limit L less than 1, then that series converges absolutely. However, if that limit as n approaches infinity of the nth root of the absolute value of a sub n is equal to some limit greater than 1, or the limit is equal to infinity, then the series diverges. And then finally, if that same limit is equal to 1, then the root test is inconclusive, and you will need to try to use another test to determine if your series converges or diverges. Okay, so if we go back to our example, if we use the root test for this series, we will have the limit as n approaches infinity of the nth root of the absolute value of 1 divided by n to the power of 3n, right? That expression is a sub n for this series. Okay, and so we want to evaluate this limit, and in order to do so, we first need to simplify a few things. Firstly, we have these absolute value bars, which really aren't going to do anything to this expression. It's already going to be positive for all values of n, since we have n raised to the power of 3n, and both of those n's are only going to be positive values from 1 to infinity. And so we know that we can remove those absolute value bars, and then the other thing I'm going to change is I'm going to rewrite this nth root to be the power of 1 divided by n. And I'll explain why we can do that, but first I'm going to write out that step. This is going to be equal to the limit as n approaches infinity of 1 divided by n to the power of 3n to the power of 1 divided by n. Now the reason we can do that is if you remember, let's say we had the cubed root of x, that would be the same as taking x to the 1/3 power. If we had the fifth root of x, that would be the same as taking x to the 1/5 power, just like the square root of x would be equal to x to the 1/2 power. And so in the same way, the nth root of a value, such as x, would be that value x to the power of 1 divided by n. That's just another way to write that out, so we can more easily see how we can simplify this expression raised to that power, or that value underneath this nth root. Okay, and so what we can do is take the 1 divided by n power of the numerator and denominator, and then simplify. And so if we do that, this will be equal to the limit as n approaches infinity of 1 to the power of 1 divided by n divided by n to the power of 3n times 1 divided by n. Right, when you take a value raised to a power to another power, you can multiply those powers or multiply those exponents. And so that's why we have 3n times 1 divided by n. And now if we simplify that, 3n times 1 divided by n will just be 3 because those n's will cancel out. And another thing to note is that 1 to the power of 1 divided by n is just going to be 1, because as n approaches infinity, 1 divided by n will become 0, and 1 to the power of 0 is 1. And so we can just remove that power and have 1 divided by n to the power of 3, right? This would be equal to the limit as n approaches infinity of 1 divided by n cubed. And now we have a pretty simple limit that we can evaluate. As n approaches infinity, this denominator is going to approach infinity, because as n gets bigger, n cubed is also going to get bigger. It's just going to get larger and larger. And so we have 1 divided by infinity, or 1 divided by an increasing denominator, which is always going to be equal to 0. And so this is equal to 0, which is less than 1, which means from the root test, we can conclude that our series converges absolutely. And so that will be our final conclusion, that this series converges absolutely. Okay, let's look at another example. All right, so here's our next example. Once again, we want to determine if the series converges or diverges, and our series this time is the sum from n equals 1 to infinity of n divided by 5n plus 1 to the power of n. And so Since we have a quantity raised to a power of n, it would be a good idea to use the root test to determine if this series converges or diverges. And so we'll take the limit as n approaches infinity of the nth root of the absolute value of a sub n, which is this expression right here. So we'll have n divided by 5n plus 1 to the power of n. Now this expression is already going to be positive all the time, so these absolute value bars aren't going to do anything. We could remove them, but this nth root and this power of n are going to cancel out, right? This would be equal to the limit as n approaches infinity of n divided by 5n plus 1 to the power of n to the power of 1 divided by n. And if you multiply those powers, n times 1 divided by n is 1. And so the nth root and that nth power cancel out and just leave us with n divided by 5n plus 1. Now I'm just going to rewrite that so it's closer to our limit notation. So we'll have n divided by 5n plus 1. Okay, and so now we have a fairly simple limit that we should know how to evaluate. In this case, we have a limit as n approaches infinity of a rational expression where the numerator and denominator are both algebraic. In other words, we're just dealing with terms of n raised to some power. In this case, we have n and 5n plus 1. Now, when you have a limit like this, there is a shortcut that you can take to easily evaluate it. What you want to do is look at the highest power in the numerator and denominator. In this case, we have n to the first power as the highest power in the numerator and n to the first power as the highest power in the denominator. And since those highest powers are equal, this limit will be equal to the ratio of the coefficients of those two terms, right? So this limit will be equal to 1 divided by 5. 1 is the coefficient of this term, and 5 is the coefficient of this term. And those two terms are the terms that had the highest power of n. And so this limit is equal to 1 divided by 5, or 1/5. And 1/5 is less than 1, which means that from the root test, we can conclude that our series converges absolutely. And so I'll write that down. This series converges absolutely. And that is our final answer for this example. Let's look at another example. All right, next up we have this series, the sum from n equals 2 to infinity of -1 to the power of n divided by the natural log of n raised to the power of n. And we want to determine if this series converges or diverges. Okay, now once again, this series includes some powers of n, right? We have -1 to the power of n in the numerator, and we also have the natural log of n raised to the power of n in the denominator. Now this -1 to the power of n is actually going to be canceled out by the absolute value bars via the root test, but because we still have this nth power in the denominator, it's still going to be a good idea to use the root test. So we'll have the limit as n approaches infinity of the nth root of the absolute value of -1 to the power of n divided by the natural log of n to the power of n. All right, now as I said earlier, these absolute value bars are going to remove this -1 to the power of n from that numerator. It's just going to become 1, because -1 to the power of n can only be two values. It'll either be -1 or +1, and so the absolute value of that is always going to be +1. So we could rewrite this to be the limit as n approaches infinity of 1 divided by the natural log of n raised to the power of n, and then I'm going to rewrite this nth root to be the power of 1 divided by n. So we'll have this whole quantity to the power of 1 divided by n. All right, now if we take the numerator and denominator to this power, 1 to the power of 1 divided by n will just be 1, since 1 divided by n will become 0 as n approaches infinity, and 1 to the power of 0 is just 1. And so this will be equal to the limit as n approaches infinity of 1 divided by the natural log of n raised to the power of n times 1 divided by n, right? We multiply those two exponents. Now n times 1 divided by n will be 1, and so they actually cancel each other out, and we're just going to be left with the limit as n approaches infinity of 1 divided by the natural log of n. All right, and so now that we have simplified, let's take a look at this expression and see what happens as n approaches infinity. Well, as n approaches infinity, this n will get bigger and bigger towards infinity, and so that is the input of this natural log function. And as you input higher and higher values into the natural log function, it's going to output larger and larger values. So this denominator will be infinity, so our limit is equal to 1 divided by infinity, and that is always equal to 0. 1 divided by an increasing denominator, or any fixed value divided by an increasing denominator, will be 0. And so this limit is equal to 0, which is less than 1, which means that from the root test, we can conclude that our series converges absolutely. And so I'll write down that final conclusion, that our series converges absolutely. Okay, let's look at another example. All right, so next up we have this series, the sum from n equals 1 to infinity of 1 divided by n minus 1 divided by n squared to the power of n. And we want to determine if this series converges or diverges. All right, now since we have a quantity raised to a power of n, it's going to be a good idea to use the root test for this series. As soon as you see some quantity raised to a power of n, that should be a huge indicator for you that using the root test will be the most efficient way to determine the convergence of that series. So we'll take the limit as n approaches infinity of the nth root of the absolute value of 1 divided by n minus 1 divided by n squared to the power of n. All right, and so now to simplify, can we remove these absolute value bars from this expression? Well, if you look at this quantity here, we have 1 divided by n minus 1 divided by n squared. This is never going to be a negative value because our values of n are only values from 1 to infinity, and so n squared is always going to be a bigger denominator, and the bigger denominator for a fraction will make it smaller than the other fraction, and so this difference will always be a positive difference. It's not going to be negative, and so we know for a fact that that positive value raised to a power of n will always be positive. So those absolute value bars are not necessary, and so this nth root is going to cancel out with this power of n. And so we're just going to have the limit as n approaches infinity of 1 divided by n minus 1 divided by n squared. All right, and now we're left with a pretty easy limit that we should be able to evaluate. As n approaches infinity, we have 1 divided by n and 1 divided by n squared. Both of these terms are fixed values divided by increasing denominators. As n approaches infinity, we have infinity in this denominator and infinity in this denominator. And so 1 divided by infinity is 0, and so we have that this is equal to 0 minus 0, which is equal to 0, which is less than 1. And so from the root test, we can conclude that this series is a convergent series. Specifically, it converges absolutely. And so we'll say that this series converges absolutely. Okay? All right, so here's our next example. We want to determine if the series converges or diverges, and our series is the sum from n equals 0 to infinity of e to the power of negative 9n. All right, now the first thing I'm going to do here before we decide to use any test for convergence is make this negative exponent positive by moving this value to the denominator. So this series will be equal to the sum from n equals 0 to infinity of 1 divided by e to the power of 9n. And now that exponent is positive. Okay, and so now I can see that we have a series that includes a power of n, right? We have e to the power of 9n. And so we should be able to determine if this series converges or diverges by using the root test. All right, so if we look at the limit as n approaches infinity of the nth root of our sequence from the series, we'll have the absolute value of 1 divided by e to the power of 9n. This expression is always going to be positive because e is a positive value raised to a power of 9 times n, where n can only be values from 0 to infinity. So we can rewrite this to be the limit as n approaches infinity of 1 divided by e to the power of 9n without the absolute value bars, and then I'm going to rewrite this nth root to be the power of 1 divided by n. All right, now if we simplify further, we can take the numerator and denominator to this power of 1 divided by n. 1 to that power is just going to be 1, right? Because as n approaches infinity, 1 divided by n becomes 0, and 1 to the power of 0 is just 1. So this is equal to the limit as n approaches infinity of 1 divided by the denominator raised to that power. And so we're going to multiply those exponents, so we'll have e to the power of 9n times 1 divided by n. And now those n's will cancel out and leave us with a power of 9, and so we have the limit as n approaches infinity of 1 divided by e to the power of 9. All right, and now the limit of a constant is just equal to that constant, so the limit will be equal to 1 divided by e to the power of 9, right? There were no more n's anywhere in this expression, so it was just a constant. And now, is this value of our limit less than or greater than 1? Well, if you look at e to the power of 9 in your calculator, it's approximately equal to 8,103.1, which is a pretty big number. And so if you're dividing 1 by a pretty big number, obviously that's going to be less than 1. And so this limit is less than 1, which means that from the root test, that our series is absolutely convergent. All right, so this series converges absolutely. Okay, that is the conclusion that we can make from the root test for this series. All right, so for our next example, we have this series, the sum from n equals 1 to infinity of n divided by 1000 to the power of n. And we want to determine if this series converges or diverges. All right, so now once again, we have a series where we have some quantity raised to a power of n, and so it's going to be a good idea to use the root test. And so we'll take the limit as n approaches infinity of the nth root of the absolute value of a sub n, which is going to be n divided by 1000 to the power of n. All right, now n divided by 1000 to the power of n is always going to be a positive value, since our values of n can only be values from 1 to infinity, so we know that this will be positive, so those absolute value bars don't matter, we can remove them, and so we'll have that this is equal to the limit as n approaches infinity of n divided by 1000 to the power of n, and we're taking that to the power of 1 divided by n. All right, but now the nth root and the power of n will cancel each other out, and so we're just going to be left with that quantity, or that rational expression, of n divided by 1000. Now let me just rewrite that so that it's next to the limit notation here. Now we have the limit as n approaches infinity of n divided by 1000, and so now we have a pretty simple limit that we can evaluate. As n approaches infinity, this n will approach infinity, and so this is equal to infinity divided by 1000, and dividing an infinite number or an increasing number by any value isn't really going to affect that increasing value. It's still going to be increasing, it's still reaching towards infinity, and so this limit is just equal to infinity. All right, and so since the limit of the nth root of the absolute value of a sub n from our series is infinity, it's not less than 1 like it has been up until this point, this series does not absolutely converge, it instead diverges. And so that will be our final answer. This series diverges. Okay, let's look at another example. All right, next up we want to determine if the series converges or diverges. For this series, we have the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 times n plus 2 quantity to the power of n divided by 3 to the power of n plus 1. All right, now in both the numerator and denominator of this series, you can see that we have some value raised to a power of n, right? We have n plus 2 to the power of n and 3 to the power of n plus 1. And not to mention that this negative 1 is raised to the power of n plus 1 as well, but we're not so much worried about that because the absolute value in the limit for the root test is just going to eliminate that. But since we have powers of n elsewhere within our series, it's going to be a good idea to use the root test. And so we'll look at the limit as n approaches infinity of the nth root of the absolute value of negative 1 to the power of n plus 1 times n plus 2 to the power of n divided by 3 to the power of n plus 1. Now, as I said earlier, these absolute value bars are going to eliminate this negative 1 to the power of n plus 1, because negative 1 to the power of n plus 1 can be either -1 or +1, and so the absolute value of that is just always going to be +1. Now for the rest of our expression, we have n plus 2 to the power of n and 3 to the power of n plus 1. Both of those are always going to be positive for the values of n we're working with, and so they're going to remain unchanged. So I'm just going to rewrite this limit. We'll have the limit as n approaches infinity of n plus 2 to the power of n divided by 3 to the power of n plus 1 to the power of 1 divided by n. I'm just rewriting that nth root to be the quantity to the power of 1 divided by n. All right, now before I take the numerator and denominator to that power, I'm going to want to do something else first. We're going to want to simplify this a little bit further by splitting up this power in the denominator. All right, whenever you have a value raised to a power where you're adding terms within that power, such as n plus 1, you usually want to split that up before you take the nth root of the numerator and denominator for the root test. Okay, and so remember, 3 to the power of n plus 1 will be equal to 3 to the power of n times 3 to the first power. We just take each of those terms and make them the powers of 3 and multiply those two values together. Right? Essentially what we're doing here is reversing the process of combining exponents when we're multiplying like bases, just like x squared times x to the fourth power is equal to x to the sixth power because we added the exponents. The same thing is occurring here where 3 is the base instead of x, and we add the exponents to get n plus 1. And so we can reverse that process and split up those exponents. Okay? So what we'll have, instead of 3 to the power of n plus 1, is 3 to the power of n times 3 to the power of 1, which is just 3. So I'm going to remove that exponent. Okay? So now we can take the 1 divided by n power, or the nth root, of the numerator and denominator. Just make sure that when you have two values multiplied together, that you take the nth root of both of those parts, not just one or the other. All right, so what I mean by that is that this is equal to the limit as n approaches infinity of n plus 2 to the power of n times 1 divided by n, divided by 3 to the power of n times 1 divided by n, times 3 to the power of 1 divided by n. All right, we took the nth root of all three of these parts. The numerator, 3 to the power of n, and 3. Okay, so now n times 1 divided by n is just going to simplify to be 1, and the same is going to occur down here for this 3. We have n times 1 divided by n. All right, so those exponents will cancel out, and we will be left with this. We'll have the limit as n approaches infinity of n plus 2 divided by 3 times 3 to the power of 1 divided by n. Okay, so now if I clean up my work, let's see if we can evaluate this limit now that we have done some simplification. And so as n approaches infinity, we have n plus 2 in the numerator. So we just have infinity plus 2, which will be infinity. This whole numerator is just going to increase towards infinity. So we have infinity in the numerator. And then in the denominator, we have 3 times 3 to the power of 1 divided by n. Now 1 divided by n, as n approaches infinity, will be 0 because we have 1 divided by infinity, or 1 divided by an increasing denominator. So we have 3 to the power of 0, which is 1, right? Anything to the power of 0 is 1. And so we have 3 times 1 in the denominator. And so we just have infinity divided by 3, which doesn't affect infinity at all. It's still an increasing value. It's still forever getting bigger. And so dividing it by 3 is insignificant. And so this limit is equal to infinity. And so our limit for the root test is equal to infinity, which means that our series is a divergent series. So we will write down the conclusion that our series diverges. Okay? Let's look at one more example for this video. All right, so here's our last example. Once again, we want to determine if the series converges or diverges. This time our series is the sum from n equals 1 to infinity of n divided by 6 to the power of n. All right, now for this series, there are a bunch of other methods that you could use to test the convergence of this series. But for this video, we're focusing on using the root test. And so since I see that we have 6 to the power of n in the denominator, the root test will probably be able to help us here and tell us if this series converges or not. If it turns out that the limit of the nth root of a sub n is equal to 1 and our test is inconclusive, then we can just go back and use a different test. All right, but since I see that we have 6 to the power of n in the denominator, the root test should work out in the end. Okay, so let's take a look at the limit as n approaches infinity of the nth root of the absolute value of n divided by 6 to the power of n. Now, n divided by 6 to the power of n is always going to be positive because n can only be positive values from 1 to infinity, and 6 raised to a positive power is always going to be positive. So, these absolute value bars aren't needed, so this is equal to the limit as n approaches infinity of n divided by 6 to the power of n to the power of 1 divided by n. I just rewrote that nth root to be the 1 divided by n power. Alright, so now if we raise the numerator and denominator to that power, this will be equal to the limit as n approaches infinity of n to the power of 1 divided by n divided by 6 to the power of n times 1 divided by n. We multiply those two exponents of n and 1 divided by n. Now n times 1 divided by n is 1, so we just have 6 to the first power, and so that cancels out to just be 1, which means that our limit will be the limit as n approaches infinity of n to the power of 1 divided by n divided by 6. And now we can pull that 1/6 to the outside of the limit because it doesn't involve any n's, and so this will be equal to 1/6 times the limit as n approaches infinity of n to the power of 1 divided by n. Alright, now if I clean up my work here, let's take a look at what happens to this expression as n approaches infinity. We have n to the power of 1 divided by n. Now n is approaching infinity, and so that is just going to be infinity. So this is equal to 1/6 times infinity, and then infinity is being raised to a power of 1 divided by n, and as n approaches infinity, 1 divided by infinity is 0. So we have infinity to the power of 0, which is an indeterminate form for a limit. We don't know what that is equal to, and so we have to find another way to evaluate this limit. We're going to need to manipulate it in some way. Specifically in this case, since we have an exponent that we can work with, it's going to be a good idea to introduce a logarithm that will allow us to deal with that exponent. Specifically, I'm going to use the natural log function, but first we need to set this limit equal to some other value. In this case, I'm just going to say that y is equal to the limit as n approaches infinity of n to the power of 1 divided by n. Then we can take the natural log of both sides and have the natural log of y is equal to the limit as n approaches infinity of the natural log of n to the power of 1 divided by n. And the reason we do that is because logarithms, such as the natural log, have a property that allow us to move an exponent from the inside of the function to the outside, right? So the natural log of a to the power of b is equal to b times the natural log of a. We can move that exponent to the outside and multiply it by the natural log function. So, in this case, we can move this power of 1 divided by n to the outside and multiply it by the natural log. So we'll have the natural log of y is equal to the limit as n approaches infinity of 1 divided by n times the natural log of n, right? We move that exponent to the outside, so we have 1 divided by n times the natural log of n. Now if we combine this by multiplying the natural log function into the numerator, we'll have the natural log of n divided by n. So I'm going to rewrite that. We have the natural log of n divided by n. And so now, if we look at this expression as n approaches infinity, we have the natural log of n, and n is getting bigger and bigger towards infinity. And as you plug larger and larger values into the natural log function, it's going to output larger and larger values. So in the numerator, we have infinity, and in the denominator, we have n, which is approaching infinity, and so we have infinity divided by infinity, which is an indeterminate form, but this form is compatible with L'Hopital's rule. So we can take the derivative of the numerator and denominator and then try to evaluate our limit again. So we'll have the natural log of y is equal to the limit as n approaches infinity of the derivative of the natural log of n, which is just going to be 1 divided by n, and that will be divided by the derivative of n. And the derivative of n is 1, and so we have 1 divided by n divided by 1, which is just going to be 1 divided by n. Alright, so I'll rewrite this. We'll have the limit as n approaches infinity of 1 divided by n, and that is a pretty simple limit to evaluate. we know that the limit as n approaches infinity of 1 divided by n is going to be 0. We have 1 divided by infinity, or a fixed value divided by an increasing denominator, and that is always going to be 0. So we have the natural log of y is equal to 0. But remember, we set our limit equal to y, so we need to solve for y to find out what that limit is equal to. And so one more thing that we can do here is make both sides of the equation the power of e. So we'll have e to the power of the natural log of y is equal to e to the power of 0. And e and the natural log function cancel each other out because they're inverse functions. And so we have y is equal to e to the power of 0, which is just equal to 1. And so y is equal to 1, which means that our limit as n approaches infinity of n to the power of 1 divided by n is also equal to 1. And so we can replace this limit with 1. So if I clean up my work, this is equal to 1/6 times 1, which is equal to 1/6, and 1/6 is less than 1, which means that from the root test, we can conclude that our series converges absolutely. All right, so that is our final conclusion. This series converges absolutely. Okay, it took a little bit of work to get to that conclusion, but in the end, we were able to use the root test to show that this series is a series that converges absolutely. All right, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.